All right, welcome back. When we last left, we did a schematic design for a converter that takes the input 5 volts and ground reference, and then outputs positive 5 volts, negative 5 volts, and a ground reference as well. Today we're going to basically be doing the board layout part, and before we do the board design, I wanted to go back to mention one thing in the schematic. So because of the nature of this sort of demo that we're doing, almost all the signals in our demo are power signals, right? They're 5 volts, negative 5 volts, and ground, basically. So all the labels we used were power rail labels. I'm going to show you, though, what we normally do. I just wanted to show if you have a normal signal, digital signal, analog signal, something like that within your design, you're not going to use those sort of rail signals. You're just going to use a net label. So I want to show that first of all. So we still have Altium up. So again, if you had closed Altium and reopened it, you want to make sure to close out those free documents and reopen your project. So one of the big mistakes people do is they work on their project without actually having the project open. They just have those files open. So please don't make that mistake. So we're just to show how this is done, we're going to label this signal C-Fly plus. So we're going to use this net label. And if we click the net label, and one thing you'll notice is if we zoom in, zooming in doesn't help really. When anything we're dropping is in a location where it's going to make electrical contact with another signal, the little crosshairs turn red. So we have sort of faint black crosshairs, and we have bold, longer red crosshairs now. So it's pretty easy if you have a snap grid to see when that happens anyway, but it's always good to tell. You can know you're actually connecting to a signal if you see those sort of red crosshairs. So we're going to drop that label. Hit escape to exit the placement of net labels, and we're going to double click the net label, and we're just going to change this to this on the chip. This signal is labeled C-Fly plus. We'll label it C-Fly plus here too. So what that did is it labeled this pin C-Fly plus, and so anywhere else in our design we could drop another net label that's called C-Fly plus, and it would electrically connect those two. So that's just another way of showing an electrical connection when one maybe doesn't exist, or when one is not shown with a wire. So we can show with a wire, but sometimes wires get too confusing and they make our schematic ugly. So the other option is to just use those net labels. Okay, so we don't care too much about that. We can update the PCB and it'll update that signal name. It looked like we had a few other changes here too. Oh, sorry, we hadn't done that yet. Oops. Okay. So when we have our schematic design done, and it's the way we want it, what we can do is we can go, and the first thing we have to do is we have to tell the software to take all of our design that we did in the schematic layout, in the schematic window, and update that in the board window. And so what it's going to do is basically all of the components that we placed by sort of dropping these parts, all of the signals that we connected either through net labels or through wires, all of those are going to be reflected on the board side of things. So for each component we have both the schematic symbol as well as the board footprint. And so what it's going to do is it's going to take the corresponding footprint for each of our schematic symbols and place that footprint in the board, and it's going to show the signal connections between the physical pins on the board side corresponding to the connections between the symbolic pins in the schematic side. So I actually just did it. I just for some reason just did it. So, but here's the process. So once we have our schematic all annotated, it's the way we want. It looks good. First of all, one thing to note: we can also do a test to make sure our schematic is correct. So there's a couple ways to do it. Sometimes I just like to do this. Right, just compile it. It finds no errors. That's a good test. There's also a DRC. I'm not used to working with this version. That's fine. Don't worry about it. But there's checks we can do to basically, and compiling will usually do it too. It just checks for errors. So errors can be things like if there are pins that we don't have anything connected to it. if you have a pin, let's say you have a component and it has a pin and you're not going to use that pin, you're going to want to tell the software not to throw an electrical rule check error. So you're going to want to put one of these no ERC labels right where that error is going to be, just to tell the software, yeah, I know that there's nothing connected to that pin, that's what I wanted. Otherwise it's going to say there's an error. I'm looking for the ERC in this version of the software. Not finding it. Oh, that's fine. We'll get back to it later. Okay, so once we have it the way we want, we go Tools, we go Design, Update PCB Document, 2-layer PCB template. So in this case, it doesn't really let us do anything. Let's change it. Let's go back and delete everything that I just did. Let's go back to the schematic, and now we'll go Tools, Design, Update PCB. So this is showing us basically every single, it's saying everything that's different between our schematic and our PCB, and it's telling us what it's going to do. So because I just deleted all those things on the PCB side, the software is saying, okay, it looks like you don't have C1 through C3, you don't have these two ports, and you don't have this component. So it's going to add all of these components. Then it's also going to say you don't have all these signals shown. These signals, which are shown as air wires on the board design, these aren't actually represented there yet, so we're going to update those. And then we're going to sort of modify the classes of these things. So we're just going to add, basically we're going to import all of our details specified in the schematic over to the board. So we're going to execute those changes. Now sometimes you do see something in here that you don't want to change. So sometimes there's a modification that the software notices, but you actually don't want that to happen. So a lot of times, for instance, let's say you had a USB header, a USB connector, and the USB connector used slot cuts for the solder through holes. But you're using a fab that can't do slot cuts, so you change those slot cuts to round holes, to drilled holes. Well, after you do that change, the software is going to say, well, there's a difference between what's on the board and what's specified in the schematic. And the software will automatically want to sort of update, to remove the part, replace it with the original design. So this is an area where you can prevent that from happening. You can essentially prevent any change from taking place. And again, it really matters mostly when you've made a change to something. You've made a change, say, to a part that was specified in the schematic on the board. There's better ways to do that. In general, if you see something like that, it's usually good to just create a new footprint for the part. But if you're sort of in a hurry and you change it, you can make sure you don't change it back here. Okay, so we're going to close that. So it automatically changes us to the board after we do those changes. And you'll see what it does. It throws this black region. So again, I'm just right-clicking to sort of move the screen around, and I can control scroll wheel to zoom in and out. So it moves all of our parts off of our actual board. This black area is the area that we designate our board design to be. If we hit the 3 button, we can see what this looks like three-dimensionally, right? So the 3 button, so I'm doing control, I'm doing shift right-click to move the 3D view, and control right-click to zoom in and out. So you see the green part is where it says our actual fiberglass PCB is going to be. It put all of these components off of that. So all of those components are off of our actual board. So if we hit the 2 button, we go back to our design. And what we're going to want to do is move all of these parts into our actual board. And the reason it puts the parts off the board is so that it doesn't mess with anything you've got on there, right? The software knows how you lay things out on the board is up to you. It doesn't sort of pick a place to put things. It's not really set up to do things like that, so it just leaves it off the board and says you put them wherever you want to. Okay, so a lot of times when the first thing we do with a board design is we move the components sort of generally to the region we want them to be. So for more complex designs, we might have a power regulator section, and all of those parts need to be in a certain area. We can create rooms for something like that. So we're not going to talk about those in this video, but there are ways to specify in the software all of these components must exist within this specific region of the board. But for now, we're just going to sort of just do this stuff manually. It helps sometimes to go back and look at our schematic, because a lot of times the schematic laid things out similar to the way we want them to be physically laid out on the board. So in this case, we have P1, the header P1, sort of off on the left side, and we have our inverting transformer here, and we have that P2 connector on the other side. So yeah, that's looking pretty good up to what we've got. A lot of times where it helps is when you have lots of capacitors surrounding a part. It can be a little tough to see, which capacitor needs to stay close to the pin, which capacitor is sort of more critical than the others. So here, basically, all of these capacitors should probably stay pretty close to the part. And actually, if we want to, this data sheet for this part that we had, sometimes you get lucky and they'll do this for you. It had a recommended footprint right here. So they basically say, they're sort of recommending you do the C in here, the C out here, the C fly here, and then they sort of give you a way to do this design. I'm totally fine with sort of mimicking this a little bit if we want to. So, in our board, so they had the CN over here. Our CN was C1. Sorry, I'm getting over a cold here. And our C out was C2. And our C fly was right here. Okay. So sort of roughly how they're spaced out. We'll move those in closer later. Then we'll just get one more peek at sort of how they recommend doing these footprints. So like they kind of snake this, sort of the critical one here. They kind of snake this guy around here, and that's fine. So maybe we'll do that. We'll kind of snake that guy in, but it's not super important right now. Okay, so let's maybe get this thing a little. Now, one thing you notice is I move these guys around. They move fairly fluidly. These parts move. Same with these guys. And one thing that's important is these are standard headers here. So these headers are standard sort of 0.1 inch spaced headers. And the thing with 0.1 inch spaced headers is we probably want to keep them aligned to each other on a 0.1 inch grid. So just to start to move things around into their rough positions, I like to set a grid that's fairly coarse. So to do that, we'll hit the G key. We want to stay within these imperial units, so we want to stay in the imperial unit domain. And let's set it to 50 mil. So let's set our grid to 50 mil. And you'll see now with a 50 mil grid, this guy definitely sort of snaps, between these sort of coarse grid locations. So let's put this guy here maybe. Okay, and so what's important here really is again that these headers be sort of stay on this sort of 0.1 inch grid, so we can check and make sure that these are actually 0.1 inch spaced. One neat thing to do that you can do with Altium is it kind of uses standard CAD rules where the last location that you clicked is sort of your new sort of reference location. So if we click here along this grid line, we can move the cursor all the way over here, and you see up in that top left corner, so right up here. In that top left corner, you can see that our DX is 750 mil. Well, 750 mil is not a nice clean 0.1 inch unit. So we'll move this guy over half, 50 mils to sort of make sure these guys are all completely now on a 0.1 inch grid. We could have just set our grid to 0.1 inch spacing as well, and that way we're guaranteed to have these things moved on a 0.1 inch grid. Okay, so this is sort of a good sort of general location. The next thing we're going to do is we're going to start routing these guys. So I actually might move these capacitors a little bit closer here. And I might move all of this up a little bit. Okay, so you'll notice, we can zoom in a little bit. the software shows these little light sort of gray colored wires. Those are called air wires, and they basically indicate where we have logical connections. So basically where we have signals that are shared between components. These wires connect each signal, each pad signal, with the nearest pad of the same signal. So it's a good way of just sort of quickly visualizing how close we are to these different components. And maybe it can kind of help us sort of rotate parts if we need to, adjust things to sort of minimize the amount of air wire crossings, because ultimately the number of air wire crossings we have are going to kind of define the number of sort of routes that we're going to have to sort of cross over one another, either by running to the other side of the board or by sort of snaking things around. So minimizing air wire crossings is a quick way to kind of save yourself some hassle later with routing. Another thing is we have these labels here. We kind of just want to get them out of our way for now. So ultimately they're a good thing to keep on the board because they help us do assembly. It's not such a big deal here because all the capacitors are the same value. But we don't want them sort of getting in our way. Sometimes they're a little bit annoying. You can actually hide all of them if you want to. You can, if you take apart and right click and go find similar objects, and we just do component. So this is basically means we're gonna select all components. So after we do sort of a find similar objects, it brings up this PCB inspector. We can always access the PCB inspector down here if we want to. So if we have multiple items selected, the PCB inspector will let us sort of change parameters on multiple items that are selected. So what we're going to do just quickly, just to clear things up a little bit, we're going to unclick this show name. And that got rid of those just for the purposes of our routing. So we kind of got them, we'll put them back later. But okay, so let's start routing this. Generally with routing, you want to start with power. Unless your design, if you have a multi-layer board design, there's a good chance you have a whole plane that's just your power and ground, or maybe you have to have multiple sort of regions that are different sort of power signals. But in this case, we're doing a 2-layer board. It's a good idea sometimes to start by moving your power around. The power signals are going to carry typically the highest currents, and so they're going to have sort of the biggest effect on noise, and they're going to require sort of the largest signals, and they're the signals you're going to want, the largest trace widths, and they're also the signals that you're going to want to spend the least time sort of dropping, back and forth between the two sides of the board. So we'll just start with the ground signal. So first of all, actually, kind of looks like I'd like to flip this guy. Looks like that's going to be a little bit easier now. Okay, so let's start routing. So the first thing we want to do when we route is we want to choose what layer we want to start routing on. So let's start on the top layer. I wonder if I can do this whole board on the top layer. We'll see if we can do it. So start on the top layer. We're going to go just click this layer button. You can scroll through all the layers. We have a lot of layers selected by default for these projects. Most designs you do won't use all these layers. We just have them all on. The default template that we use just has all these ones turned on. So let's go top layer. And with top layer selected, we can then select the interactively route connections tool. And then we can click on any pin we want. And when we click on that pin, it highlights all of these signals here. So it's highlighting these signals that we're going to have to connect using this guy. So we can start, as we start sort of, after we've clicked the pad, when we move this around, this is an interactive route. So as we sort of move this mouse to show where we want the path to go, the software does its best job to try to make the connections that it thinks we're trying to make without interfering with anything else. There's some pros and cons of this. One thing to do is be careful sort of how far you let this go before you sort of lock in the route. So I'm going to show how that works. Oops. Well, let's route to this guy here. Nope, our grid is way too coarse right now, so we're going to drop our grid down to 10 mil for the purposes of routing. So we'll connect to this guy here. And you'll notice after we clicked that, I moved the cursor here and clicked it, but it didn't make the connection all the way to the pad. So this option is, there's a couple different options we have for routing. This option basically has two different segments that it routes. It has sort of the early segments while you're doing this routing, and then it has the closer segments. So, and if you look down here, we see there's one, that first little hash marked faint red section of trace has hash marks in it. That's when we click, that's the part of our trace that it's going to lock in. The other section, which is just outlined with a red line, that section is, and I can zoom in a little bit. The section just outlined with a red line, that's even after we click, that's still going to move. So I'll show you what that does. So let's go back. We didn't want to get here. Okay, so now we have that hashed section, and if I click, only the hashed section actually becomes a trace. And then if I do it again, only the hash section becomes a trace, and the next segment of our route becomes the next hash section. So we're going to click there. Now the nice thing about this is when we do it like that, it kind of lets the software can help us with some things. Like for instance here, the software can automatically calculate what that 45-degree angle has to be to sort of meet us at the pad. Let's say we hadn't done that. What if we just clicked it here? Well, now we're going to have some weird connection to get there, right? So what if this happens though? We clicked a little bit early, we got a little excited, we placed a wire somewhere we didn't want it to go. We want to undo that placement. You can hit the backspace key. If we hit the backspace key, it'll undo that last sort of locked in route there. So then we can go back and place this wherever we want. Now one thing to note also is these traces that we just did here, these are fairly thin. I mean, for power traces, it's probably not a big deal for this particular design because we're talking about a low current design. But usually we're going to want thicker traces than this. So let's route something else, possibly using thicker traces. So we have we click, we're going to route this net C31, which is our C-flag negative signal. We just didn't label the signal, so the software picks a label for us. And we see, we can see the trace. Yeah, we could probably go a little bit thicker for that. So let's hit the tab key. When you hit the tab key, it pops up this sort of, and anytime you have something selected and you hit the tab key, it's going to sort of pop up the menu for changing aspects of what you're doing at that time. So in this case, we have a width. The width is specified at 10 mil. That's probably okay, but we can probably go bigger than that. Now notice the limits of that trace width are going to be set by whatever fab you're using. So a lot of low-cost prototyping fabs are limited to 6 mil. So you want to make sure not to go below 6 mil for these. There's also rules that you can set for your entire system that sort of prevents you from going smaller than whatever your limits of your fab are. Let's just change this for now to 18. And that looks good. Oops. Okay, so now we want to get this negative 5 volt signal here out, but we have a little bit of an issue, and that issue is if we try to route this, it kind of runs out of space here. Now the router will automatically it can push this signal if we sort of force it to, but you'll see right now it's kind of having a little difficulty making its way over there. And again, it will bully the others. It will push through if it has to, and we can change those settings on how it routes. For now, let's hit escape. And I'm going to show you how you can manipulate these tracks after you've already placed them. So in this case, we got to give a little bit more space in here for that signal to route. So we're going to take this section, this trace, and we click it once, and then we click in this area. We don't want to click on the endpoints or on this midpoint. And if we move this guy down, it's going to automatically extend those other segments as needed. And then we can also do the same here. If we click here, we can sort of, it'll automatically make that space happen. And then we can go back to our route. Okay, looks pretty good. All right, now we got to get a couple more signals, and that's all. Okay, so now it looks like our board is fully routed. And there's one thing I don't like about this. What I don't like about this is this ground wire, right? We did this initially and we didn't make this guy very thick. And this is, this happens a lot. Typically what you do is you'd set the thickness for whatever it needs to be before you start placing the wire. But this is a ground wire, and there's a lot of times there's fun stuff you can do with ground wires. Ground signals are generally sort of a common reference throughout your entire design, and so it's very common to use what's called a ground plane. That's a sheet of copper. Anywhere you can use copper, you make that copper connected to your ground signal, and that minimizes the resistance along the ground signal. It prevents sort of voltage drops across your ground signal, which sort of minimizes noise and keeps this reference constant across your board. So we're going to place a plane. We're going to do a ground plane really quickly. We could have sort of fattened up this connection. And one neat thing you can do, by the way, is you can go, there's a way to select, if you go select connected copper, it'll select all, that whole sort of copper net, which is kind of a neat thing that you can do. But let's do a ground plane. So to do a ground plane, we go to Tools, Place, Polygon Pour. So we can name this. We're going to name this guy. So Polygon Pour is basically, it's a polygon of a single signal connection, which is going to fill the entire region where it can without interfering with other signals. So we're going to call this guy just ground plane. It's going to be on the top layer. Again, we're trying not to use the bottom layer, just for no real reason, just for fun. And then we'll do connect to net ground. And then this tells us basically, when we make this plane, do we want it to, we have some options here, right? We can have it only connect to polygons of the same net, which will basically mean that it will avoid actually merging with this ground trace here. Or we can say don't pour it over the same net object, which basically means this is just going to be a unique signal. So it's going to be a plane which is not actually connected to any established signals we have on the board right now, but it still will be specified as a certain signal. Or we can do pour over all same net objects, which is where anything in our design which has the same signal, which carries the same signal, will be merged with this polygon plane. And that's what we'll do in this case. There's the option to remove dead copper. There are pros and cons of doing this. If you're not the one fabricating the board and it's not your copper, you might not care so much. Or some fabs, the way they fab things, they prefer you to leave extra copper because that copper they don't have to etch off. It all depends on the process, but there's pros and cons of it. It's kind of up to you. So now we have to specify the ground plane. Let's go back to a coarse grid. So I'm going to hit G, set my grid at 50 mil. Nope, I'm going to set my grid at 25 mil. Okay. So this is a polygon, so we basically are going to make it as big as we want. In this case, I think this is pretty good. Okay, I hit escape, by the way, to escape that polygon placement. And you'll see what this did is it created a ground signal that, again, the plane poured over all of those ground traces that I had already done. So why did I, why does it have these little connections here? There's these little, our pads are only connected by these little sort of crosshair connections. That's called thermal relief. And the problem with ground planes are great electrical conductors. They're also great thermal conductors. And having a good thermal conductor is not always a good thing. Especially if you have like a through hole here where you're going to solder a wire to. It can become very difficult to, if your board is cold, it can be very difficult to solder a part onto a ground plane because that ground plane is so good at sucking heat away from the tip of your soldering iron. So in this case, it sort of does these thermal reliefs, which basically, it still gives you good electrical conduction, right? These are very short, so there's still fairly low resistance. But it also gives you good thermal insulation, so you can actually solder to these things. So now that we have that, it looks like our design is done. It looks like this is good. This will work for us. There's a couple more things we want to do, though. One is let's put back those annotations. So let's go find some more objects. Let's just choose all, not pads.
Publicly owned.
Okay, so we've selected all of our components again, and let's put these names back in. Show name. Okay. So now we want to move these things around as we see fit. So let's see one. You know, we even have enough space. Just put it here. We got U1 here. U1's going to be pretty easy to identify because we only have one. We only have one actual component. C2. Let's move C2 down here. C3. Actually, I want to put C3 over here and U1 over here. Now you'll notice it kept collecting the ground plane. There's a couple ways to avoid that. If we're just working on these labels on the silk screen, we can just select the top overlay layer, and now it's going to give preference to selecting things on the top overlay. Okay, so that's not great, but it's pretty close. It's pretty good. So we've sort of moved our labels. Now we actually need to specify our board shape. So if I hold Control and scroll wheel, I can zoom out. You see our board is currently defined as this gigantic area here. We don't need it to be that big. So what we can do is we can hit the 1 key, just hit the number 1, and that brings us to sort of this board outline definition. From here we can go Design, Redefine Board Shape, and this is just going to let us just sort of click around and pick an outline that defines the outline for our board. Hit Escape. And so we now redefined our board shape. So you'll notice we don't have that big black box anymore. And more importantly, if we go to the 3D view, by the way, the 2 key takes us back to this view. If we go back to the 3D key by hitting the 3 key, now our board looks much smaller here. So now our board looks a lot teenier. Okay, so, you know, I don't quite like that. I don't want the board shape to be all the way up against the edge here. It's going to cut off that silkscreen. It might look kind of ugly. So what I'm going to do is I'm actually going to set my grid to 25 mil, redefine board shape, and just make it a little bit bigger. Okay, that's a little bit better. Okay. Now, different fabs too. Some fabs don't like you ever letting the board outline. Sometimes they don't ever let you, or like you putting like a plane right up against the board edge. The fab that I use is okay with it. But just note, if you do have a plane that goes right up against the edge of the board, there's probably going to be an exposed little copper edge there when it gets cut. There'll be a little bit of copper shown there. So we've defined our board outline, although that doesn't necessarily mean that that's actually our board outline. So this is the outline as shown in the software, but when we export this, it doesn't necessarily, this sort of Altium board outline is used a lot of times for viewing, you know, for displaying it when you're in your 3D view, the 2D view, for limiting where routes are. So if you do like an auto route, it'll keep the routes within this sort of board area. But it doesn't necessarily tell a fabrication facility where the board outline is. So to do that, we can just specify a keep out. So we're just going to select the keep out layer. We're going to just do place line. Now, one thing really quick too, as I'm placing these lines, you see they're kind of doing this 45-degree angle thing here. But I have other options. If I hit the space bar will show me other options. So in this case, before it was doing a 45 then a straight, now it's doing a straight then a 45. The other thing we can do is we can do shift space bar, and that changes the style. So in this case we're doing 45-degree sweep, straight 90 degrees, 90-degree sweeps, just straight angle, whatever it is, and then we're back to our 45. So if we want to go back to straight, or if we want to go back to 45 and then straight, we hit the space bar again. So again, it was shift space bar to move styles, space bar to change, sort of to flip the kind of which axis sort of gets corrected first. And then hit escape. Okay, so it's looking pretty good. We're almost done here. One thing we'll do next, though, is we will make sure that everything is correct. So we always want to sort of verify. We want to do a rule check to make sure we haven't broken any rules. So to do that, we can go Tools, Design Rule Check. Now, I'm not sure we have the right specifications, but the design rule is basically you have to set rules in Altium for the design rule to know what's a rule violation. Generally, you want to set rules defined by your fabrication facility. So we'll just assume the defaults are correct. I'm not sure that's true. We'll run the rule check. When we do that, it'll pop open a window here. Looks like we have one rule violation. That's not necessarily fatal. We'll just check and see what it is. So it is a silk to solder mask clearance. So basically they're saying if your silk screen is too close to a solder mask, there's a chance the silk screen won't print correctly. So we can see where that is, but I don't really usually care about these. Silk to silk clearance, silk to solder mask. Unless you really need a perfect silk screen that has no chance of getting interrupted by a solder mask opening, I don't worry too much about it. So if we click on that error though, it'll zoom into where it is. So it looks like, yeah, that C2 is maybe getting a little bit too close there. So that's fine. We'll set our grid to something fine and move the C2 a little bit. Not that much. Yeah, maybe that'll take care of it. Put our grid back. And, oh, look at that. Now we have no warnings, no violations. So let's go back, and I'm willing to call that a good enough board design for now. So I hope you learned about sort of placing and routing, moving components, routing components using Altium. Next time we'll export these for fabrication. So thank you.